draw the transfer characteristics of a clipper circuit shown in figure. Now in this circuit there is one difference in our basic clipper circuit and this circuit, that up to now we didn't have this load resistor in the circuit, but in this circuit we have this load resistance. This load resistance will affect the operation, and this clipper circuit will behave something different, like from our the previous circuit. Now by observation we'll say that this diode will be forward biased if this 10 sin omega t, which is a sinusoidal voltage which goes up to 10 volt and in negative to minus 10 volt. This diode will be forward biased if this sinusoidal voltage goes above 6 volt. It is seen from the circuit, but this circuit has operation bit different from this concept. Initially we assume that the input voltage Vi is less than 6 volts. If input voltage Vi is less than 6 volt, then it is confirmed that the diode is reverse biased. If diode is reverse biased, then we'll replace this diode with open circuit. If this diode is reverse biased, we have replaced this diode with an open circuit. Now in the previous circuit we have seen that if diode is reverse biased open circuit, there was no current in the circuit, but in this circuit we have a current through these resistances. If a current is flowing through these resistors, then we can see that there will be some drop across this resistance and there will be drop across this resistance, and we are interested in the voltage which is reaching at this point because it will determine when the diode will be forward biased. Now this voltage will be equal to V, and we can see that we have this 10 sin omega t here, this R equal to here, and this RL equal to here, and this will be considered as ground. And at this point we are calculating this voltage V, and this voltage V is itself equal to output voltage, because output voltage and this voltage are connected through the wire, so this will be the output voltage. But still now we are interested in the value of this voltage V. Here we have applied this input voltage Vi. This potential divider network will divide this input voltage and it will be written as Vi into RL upon R plus RL. Now RL and R both are equal to 1 kilo ohm, so Vi into 1 divided by 1 plus 1 equal to Vi by 2. Vi by 2 means only half of the input is reaching at this point, so this voltage V is equal to Vi by 2. Now we know that the diode in this circuit can be forward biased if this voltage V is greater than this voltage 6 volt. So if V is greater than equal to 6 volt, then only diode can be forward bias. If V equal to Vi by 2, so Vi by 2 is greater than equal to 6 volt, and if Vi is greater than equal to 12 volt, then only it is possible that this diode D will be forward biased. And we know that the applied voltage is only 10 volts, then the output is only 10 volt, it cannot reach up to 12 volt. So diode in this circuit will be reverse biased always. Diode in the circuit will be reverse biased always. So here we'll say that for all values of input voltage, D is reverse biased, and output voltage V naught is equal to V equal to Vi by 2. Now we'll draw the transfer characteristics for this Vi and this V naught. For all values of input voltage, output equal to Vi by 2, which is a straight line with slope of 1 by 2. This is the transfer characteristics for this. Now the next example, draw the transfer characteristics for the circuit shown below. Now in this circuit, again it is looking like the previous circuit. We'll start, we know that if Vi is less than 3 volt, then it is not possible that diode will be forward biased. So for Vi less than equal to 3 volt, diode will be reverse biased. If diode is reverse biased, we will replace this diode with an open circuit, and again there is a path for current flow in the circuit, and the current will continue to flow, and at this point the voltage V will be equal to Vi by 2, because these two resistances 1 kilo ohm 1 kilo ohm are same. So V equal to Vi by 2. Now we know that diode D will be forward biased only if V is greater than equal to 3 volt, that is Vi by 2 is greater than equal to 3 volt, that is Vi is greater than equal to 6 volts. If Vi is greater than equal to 6 volt, then only the diode will be forward biased. Now sorry, I forget to write this input voltage. This input voltage is 10 sin omega t. So for now we know that for Vi greater than equal to 6 volt, it is possible that the diode will be forward bias. So now we'll draw the table for this. If Vi is less than 6 volts, then diode D will be reverse biased. And if diode is reverse biased, we will replace it with an open circuit, and if it is replaced with open circuit, this output voltage V naught will be equal to this V voltage. So V naught will be equal to Vi by 2. For Vi greater than equal to 6 volt, this diode will be forward biased and will be replaced with short circuit. If this diode is replaced with short circuit, between these two terminals there is a battery connected which is equal to 3 volt. So V naught equal to 3 volts. Now we'll draw the transfer characteristics for this. This time the break voltage is 6 volts. For Vi less than 6 volt, output equal to, or for Vi greater than equal to 6 volt, output is 3 volts only. So this will be the graph. And for Vi less than 6 volt, output equal to Vi by 2. That is a straight line passing through origin. Now we'll see the next example which was asked in electrical engineering gate paper. For a diode, the equivalent circuits are, when it is forward biased, it is replaced with a 0.7 volt battery and a resistor RF, value not given. When it is reverse biased, cathode is at a higher potential than anode, then it will be replaced with an open circuit, and this circuit is given. Now we are asked to draw the output waveform in this question. There are 4 waveforms given in the problem. We have to choose the right option. Now these 4 options are given in the problem. We have already seen 2 problems of this kind. We know that when Vi is less than 5 volt, it is confirmed. In fact, this diode also require a 0.7 volt to operate in forward bias. So the total voltage will be 5.7 volt. So if Vi is less than 5.7 volt, it is confirmed that the diode will be reverse biased. And if this diode is reverse biased, this will be replaced with an open circuit. And now as these two resistances are same, so V equal to Vi by 2. And we know that if Vi by 2 will be greater than equal to 5.7 volt, here we are taking 5.7 volt because when diode is forward bias, it requires a 0.7 volt to become a forward bias, in the last 2 example we have seen ideal diodes, but this time a practical diode is given which require an additional 0.7 volt to when it is forward biased. So 5, if Vi by 2 is greater than equal to 5.7 volt, then only the diode will be forward biased. So if Vi is greater than equal to 11.4 volts, then the diode is forward biased, and we know that the input is 10 sin omega t. It cannot go up to 11.4 volts. So in this case, in this circuit, the diode will be always reverse biased. If this diode is reverse biased, then output V0 will always equal to Vi by 2 equal to V. So if input is 10 sin omega t, output will be 5 sin omega t. Up to, it will go up to 5 and minus 5. So option A will be correct. Now the next example. A clipper circuit is shown below. Here is the output voltage V0 and this is the input voltage Vi. Now for this circuit, the Zener diode has a breakdown voltage equal to Vz. Assuming forward voltage drops of the diodes to be 0.7 volt, the input output transfer characteristics of the circuit is, here four options are given. Four point three volt, 4.3 volt. This is output, input. Option B, 10 volt. 10 volt. Four point three volt, 4.3 volt. Option C, 0.7 volt, 0.7 volt, 5.7 volt, and this is also 5.7 volt. And the last option, 1 volt, 1 volt, 10 volt, and this is 10 volt. So these four options are given for the circuit, and we want to calculate the correct transfer characteristics for the circuit. Now in this circuit, this Vz is given equal to 10 volt, and the forward drop across the diode is 0.7 volt, which means if diode is forward biased, it will consume a 0.7, or if diode is forward biased, there will be a voltage drop of 0.7 volt across the diode. So if diode is forward bias, we will have to replace this diode with a 0.7 volt battery. Now we'll start solving this problem. We'll draw the circuit again. Now in this circuit, Vz is given equal to 10 volt. The diode Vz, the diode, Zener diode, if this is a Zener diode and for this Vz is given, if the voltage across diode is greater than equal to Vz, reverse voltage with this polarity, then diode will operate in breakdown and we will replace this diode with a battery equal to Vz. And if this diode is forward biased, means with this polarity, then this diode will be forward biased and it will be replaced with a 0.7 volt. This is how a Zener diode will operate. Now first, initially we assume that Vi is 0 volt and we will increase this Vi above 0 volt. If Vi is greater than 0 volt, it is clearly seen that this voltage, this Vz, this Zener diode is reverse biased. It can operate in reverse bias also, but for that the voltage across diode must be greater than its Zener voltage, that is 10 volt. So for when input is less than 10 volt, this diode will be reverse biased and it will be out of breakdown, so it will be replaced with an open circuit. If it is in breakdown, then only we can replace it with a battery equal to Vz. Now Vi, if Vi increases and if it becomes greater than equal to 5 volt, then diode D, this diode D and this diode Z, this diode D can be forward biased, but it is given that the diode has forward drop of a 0.7 volt, so it will require a 0.7 volt extra voltage to become forward bias. So when Vi becomes greater than equal to 5.7 volt, then only we get this diode equal to forward bias. So when Vi is greater than equal to 5.7 volt, then diode D is forward biased and diode Z, Zener diode, is reverse biased but out of breakdown. And if this diode is forward biased, we will replace this diode with a battery with a battery with battery of a voltage 0.7 volt. And if this is replaced with a battery, we can see that the between output terminal there are two batteries, 5 volt battery and 0.7 volt battery, so V0 will be equal to 5.7 volts. It is clearly seen that output V0 equal to 5.7 volt. Now for Vi greater than equal to Vi greater than 5.7 volt, for all the voltages the output voltage will be equal to 5.7 volt. That is, the voltage across this Zener diode will always be 5.7 volt. It cannot exceed 10 volts. So Zener diode will not enter into breakdown for any voltage of input, for any input voltage. Now if input is in negative half cycle, if it is in negative half cycle, then this diode will always be reverse biased. There is no chance for this diode to be forward biased in negative half cycle. But this Zener diode can be forward biased, but it is given that this diode has a voltage drop of 0.7 volt when it is forward biased. So this diode will be forward biased only if the input voltage is less than minus 0.7 volt. So if input Vi is less than equal to minus 0.7 volt in negative off cycle, less than minus 0.7 volt, then this Zener diode will be forward biased, while this diode will be always reverse biased when it is in negative half cycle. So in this case, this Zener diode will be replaced a battery with a battery of voltage. Sorry, the polarity will be different. Anode will be positive, so it will be replaced with a zero point 0.7 volt battery, while this diode will be reverse biased. And in this circuit we can see that the output voltage is equal to 0.7 volt. And the last case, if Vi is greater than minus 0.7 volt but less than 5.7 volt, both the diodes will be reverse biased. None of the diode will operate, and output will be equal to input Vi, because both will be open circuited. And if both are open circuited, this input voltage will reach up to output voltage. There is no path for current flow, so there will be no voltage drop across this diode. Now the transfer characteristics for this break voltages are, there are two break voltages, 5.7 volt, minus 0.7 volt. For Vi less greater than equal to 5.7 volt, output equal to 5.7 volt. For Vi less than minus 0.7 volt, output is equal to minus 0.7 volt. It will be minus 0.7 volt. And for Vi between minus 0.7 volt and 5.7 volt, output equal to input. So there will be a straight line passing through origin. So this is the transfer characteristics